take a look at another couple more examples of optimization problems where we're trying to find the maximum or minimum of some sort of application. So in this case, we're going to look at an economic problem as well as another one involving shapes. So for this first one, we're going to look at a tour service offers the following rates. We can charge $200 per person if there's 50 people, and that's going to be the minimum number of people that can go on the tour. So if there's less than 50, then the tour just wouldn't go. And for each additional person, up to a maximum of 80 people, the rate's going to be reduced by $2 per person. So it's getting cheaper per person. And also, it just costs $6,000. That's the fixed cost plus $32 per person to actually conduct the tour for the company conducting the tour. So we want to figure out, as the company, how much or how many people would be like the best number of people to maximize the profit on the tour, taking into account the fact that the tickets get cheaper if there's more people on the tour. So what we need to remember is that profit, the money that we're going to be making in the end, is just the actual revenue. So that's how much we take in, and take away the actual cost. That's how much it takes to run the business. So profit's what we're left with. And so what we want to do is we want to define our variables. We want to define, let's define R to be the revenue. The revenue. And let's let C represent the cost. Basically all these different portions we're going to just define, just to be clear of what we're doing. P is going to represent the profit. Okay, we're not quite done yet with our variables though. There's one last thing that we need to take into account. The fact that there could be a different number of people showing up, there could be a different price of these tickets. So what we're going to focus in on is the fact that these tickets, the rate per person, is being reduced by $2. What we're going to say is, like, we're going to ask the question, how many times are we changing the price? As in, how many extra people are there? So what I'm going to represent it as, I'm going to use the variable x. Let x represent the number of price changes, or the number of extra people. There's a couple different ways you can think about it. Okay, so let's break this down now into the revenue, the cost. We'll combine it into a profit function, and then we'll find the critical point of that profit function. So that's the idea we're going to have here. Okay, so starting off with the revenue, it's actually going to be a function of x, because it's going to depend on the number of price changes. Well, the revenue is just going to be the number of people that go on the tour times how much each of those people are spending on the tour. So let's break it down into that. So number of people times cost per person, or let's just say ticket cost. Okay. And well, what are these two portions? Well, the number of people, that's just going to be 50. That's the minimum. And we said x represents the number of price changes, which is also the same as the number of people, because for each person, or each, I should say, the number of extra people, because each person represents a discount in the price. So we're going to say this is 50 plus the number of extra people. And then the actual ticket cost, well, that's going to be 200. That's the original price. And we're going to subtract, well, it's a $2 decrease. So 2 times the number of price changes. And so this function is now going to represent the revenue. We also have a cost function. So how much does it cost to run this? And let's take a look back at our situation here. We have $6,000, that's a fixed cost, plus $32 per person. So $6,000, we're just going to have that straight up in there. Plus then 32 times the number of people. Well, we just said the number of people is 50 plus x. So we can just rewrite that down. And all of this together is going to make our profit. So profit of x, well, the profit is going to be the revenue minus the cost, r of x minus c of x. So let's subtract these two functions that we have written down. So 50 plus x, 200 minus 2x, subtract 6,000 minus 32x. So I'm just distributing that minus sign in. 32, 50 plus x. And let's just clean things up in this function. So we will expand, collect like terms, do all of that, and then we can take a derivative. So expanding things out, what we're going to get is we're going to get 10,000. We have negative 2 times 50, and that's going to be negative 100, plus 200x is going to be plus 100x. And then x times negative 2x is minus 2x squared. Minus 6,000 minus, well, 32 times 50 is going to be 1,600. And 32 times x is going to be minus 32x. Collect these terms. And if you collect the terms, you're going to get, well, 10,000 minus 6,000 minus 1,600. And let's write things in order. So negative 2x squared first. 100 minus 32 is plus 68x. And then plus 2,400. And there we have it. That is our profit function. So now that we've got a profit function, we can do things like take the derivative. So I'm just going to take a moment to add an extra page. All right, let's go ahead and take this derivative now. So the derivative is going to be, well, negative 2x squared is going to become negative 4x plus 68. We just want to find the critical point, so set p prime of x equal to 0. And so negative 4x plus 68 equal to 0. It's just a very quick one to solve here. Negative 4x equal to negative 68. So negative 68 divided by negative 4. And so in the end, x is going to be equal to 68 divided by 4 is actually just 17. So 17 is the number of price changes. Okay, but let's keep in mind the domain. Which was 50 to 80 people. So does, first of all, x equaling 17 fall in that domain? Well, 17 was the number of price changes, which was the number of extra people. So we can think of this as 17 extra people over minimum. So 50 plus 17 is going to be 67 people. Okay, so it's within that domain. Let's also check the ends. But before we check the ends, let's just figure out how much revenue this would actually result in, and double check that it's a maximum. So p prime prime, just doing a second derivative test here, it's just going to be negative 4. So always negative means that x equal to 17 is a maximum. And then let's check the ends just to make sure nothing funny is going on. So after we check the profit at 17, we'll check the end. So we'll plug in 17 into our big profit function that we had. So it's going to be something like, let's do the simplified one, negative 2 rather than our one with brackets. Negative 2 times 17 squared. Sorry, I just have to keep going back up to remember 68x and 2,400. So plus 68 times 17 plus 2,400. Okay, typing that into your calculator, take a moment, and you should get something like $2,978. So that's the profit they would make at 17. And, well, what would the profit be if they had no price changes? So either 0 price changes would mean you have 50 people, or max price changes, which would be 80 people, for 30 price changes. So we're just going to check the end values just to make sure that they're less than that. Well, let's see. So P of 0, plugging that into the function, well, P of 0 actually works out really nicely because you just have the quadratic, it's just 2400. And P of 30, this one we have to do a little bit more calculation, so negative 2 times 30 squared plus 68 times 30 plus 2400. And let's take a moment to calculate that out. And in this case, we get $2,640. Okay, so both of those, the endpoints are actually not above the critical point. So therefore, the maximum profit is $978 when 67 people go on tour. Yeah, the key to this question again, and for many of these optimization questions, is how do we set it up? Once we get it set up, it's just a matter of a derivative, maybe a derivative test in there, and checking some endpoints. But it's getting that original equation set up properly. All right, so let's take a look at another one of these shape questions where we might have multiple variables, and we're going to have to see what we can do about that. So for this shape question, we have 2,700 centimeters squared. Okay, so we see a centimeter squared. If you're taking a look at your units, you can figure out just based off the units what you're looking at. So centimeter squared, well, since it's a square in there, it's two-dimensional, so it's going to be surface area, which is two-dimensional. If you had something like cubed, well, cubed is three-dimensional, which would then be looking at volume. So just in terms of like volume kind of questions or surface area kind of questions, just geometry questions, you can take into account the units to double check what you're actually looking for. So we've got that much material, and we want to make a square box. Make sure you're looking at a square box. That'll make our lives a little bit easier with an open top. And we want the dimensions, length, width, and height. Well, length and width are going to be the same for a square. That give the largest volume. So what is the maximum volume of the box? Let's see. So let's draw a picture. Okay, let's attempt to draw a picture here. Sorry, I'm not the greatest at this drawing thing. So we've got a box with hopefully a square base. Rulers are awesome too if you have them. And this top portion is open. All right, it is also a square. So since it's a square base, all those side lengths, we'll just call it the width, are the same. Then we also have a height, and we're going to be looking at surface area and volume. So let's define some variables now. We've kind of written them on the diagram, so let h be the height. And we're looking at centimeters, so I'm going to even specify that. Let w be the width in centimeters. And we're dealing with surface area and volume, so we're given the surface area, so let SA be the surface area. And that's in square centimeters. And let V be the volume. And again, we're going to want to come up with some sort of equation in terms of a single variable, but at first, well, if we take a look at volume, So of a square base, it's just going to be w squared times h. Two variables. Can't really do a derivative with two variables. So we need to figure out how can we get one of our variables in terms of the other ones and substitute it in. So I'll just say want. I can't spell or write. Want in terms of a single variable. And that's where the amount of material we're given, that's where that's going to come into play. So we're told that the surface area is 2,700 centimeters squared. We know that because it's an open box, like an open top, the surface area, we have the square base, which is just, well, w squared. That's the base. And then we're adding on the four sides. And if we take a look at the sides are just, you have a w as your one length and the h as the other length. So the side is just w times h. So we're just going to have w times h. And how many sides do we have? Well, it's a box. There's four sides around, excluding the top and the bottom. So 4 times wh. So the four sides. Okay, so we've got our general equation for the surface area and what it's equal to. So let's set that equal to each other. And then looking at this, what is easier to solve for? Is it easier to solve for h or w? Easier to solve for the width or the height? Well, definitely the height in this case. So let's rearrange and solve for that. So divide by 4w, so 2,700 minus w squared over 4w. Right, there we've got the height. So now we want to sub in the height into volume equation. And let's go ahead and see what happens. So our volume equation is going to be now, instead of w squared h, it's going to be w squared times 2,700 minus w squared all over 4w. And in this case, the w here is actually going to cancel out one of the w's in the squared part. And let's just distribute it in. So it's going to be 2,700 w minus w cubed all over 4. All right, there we go. And this makes sense for a volume equation. Actually, your units will align because the 2,700, that's centimeters squared, times another centimeters from the width, centimeters cubed, w cubed, another centimeters cubed. You don't need to worry about that. But yeah, the equation does work out even if you're looking at the units. So now what do we want to do? Well, let's just go ahead and take the derivative. So v prime, well, since we've written our equation in terms of just w, we can think of it as a function in terms of w. So I'll just say v prime of w. Okay, so when we're taking this derivative, we can think of the 4 as a coefficient. So it's just a coefficient, so we can just leave it there. And then we can take the derivative at the top. So that's just going to be 2,700 minus 3w squared. So set that equal to 0. And we're going to, 0 is equal to 2,700 minus 3w squared all over 4. So all that matters is the numerator. And if you solve for the numerator, just have to rearrange a little bit. So move the 2,700 over, divide by -3. Oh, moving the 2,700 should be -2,700. Divide by -3, that's where your negatives will cancel out. And you're going to get w squared is equal to, well, 2,700 divided by 3 is just 900. So the square root of 900, which is just, well, well, it's actually two answers, plus or minus 30, but I mean, the negative answer for it does not make sense, so just 30 centimeters. All right, so that's looking good. Now what we could do is we can double check if that's a maximum or minimum. We're feeling like it should be a maximum, but do a second derivative. So the second derivative is just going to be negative 6 times w all over 4. And so plugging in 30 into that, it's just going to be negative 6 times 30 all over 4, which is definitely less than 0. It's a negative number. So therefore, w equal to 30 is a minimum. Or sorry, not a minimum. If it's less than, that's concave down, which would be a maximum, which is what we're asked for in the question. Okay, but it wants the full dimension, so we still need the height. So just go back into your equation. We had solved for h. You go back, we'd said h is 2700 minus w squared over 4w. So plug it into that. 2700 minus 4 times 30 squared over 4 times 30. And if you calculate that out, type it into your calculator, you should get something like 15 centimeters. All right, and there we have it. So that is a look at finding the dimensions that maximize that volume. So therefore, the dimensions to maximize the volume. So the dimensions to maximize volume. We should find the volume actually. Are h equal to 15 centimeters and width equal to 30 centimeters. But yeah, let's just take a moment real quickly. Let's get that volume. So the volume is just going to be h times w squared, as in 15 times 30 squared. So simple calculation to do. And if you calculate that out, you should get 13,500 centimeters cubed. Let's put that into our conclusion. And there we have it. There's another couple examples of some optimization problems.